Hello from the Bridge Software Institute at the University of Florida. In this video, we'll use the geotechnical design software GeoStat to demonstrate how to form variograms. Variograms are highly effective mathematical constructs that geotechnical engineers can use to summarily assess spatial correlations among sets or subsets of site data. This will be explained further later in the video. We can first navigate to our desktop shortcut and open the GeoStat software. We can then access the example file by simply clicking the open icon, which appears here as a folder. Then we can move on to our example file, which in this case is a specially created model file for demonstrating the creation of variograms. Notice here that GeoStat receives its inputs through Excel files, and whenever a model loaded in GeoStat is saved, all the inputs are saved in a formatted Excel file. The example file that we have just loaded is a synthetic dataset and is being utilized exclusively to demonstrate program-guided generation of variograms. When viewing the Project Information tab of the GeoStat UI, we can see the plan view of our site. That is the leftmost plot that displays the position of all the included boring locations where the idealized borings are evenly spaced at 1 foot increments along a constant northing. The SPT blow counts for each of the borings were synthetically generated by starting with one real-world boring and then for 50 realizations perturbing the through depth SPT blow count values to generate the 50 synthetic borings. This is a relatively large data set encompassing tens of thousands of SPT blow counts as shown, and again is presented purely to demonstrate variogram generation. For real-world data sets, it may typically be necessary to divide the site into zones, where inclusion or exclusion of a given boring for analysis can be indicated in the table located on the right portion of the Project Information tab. As we can see, all the borings are included here. When navigating the tabulated listings of the boring data, the currently selected boring location and through depth boring data are visually indicated in the plots as shown. We can now move on to the Profile tab. And here we can see both plot-based and tabular listings of the profile data across all the included borings. The data is presented such that the layered profile can be built up graphically or by input on the table, and then soil types can be assigned for each defined layer. For the simplicity in this video, we have defined only a single layer of clay throughout the approximately 100 feet of elevation change across all of the synthetic boring data, and the soil types are shown here in the notes. Within the profile plots, the horizontal blue lines indicate layer bottom elevations. This is also summarized in the table in the right portion. The table in the right portion of the tab. Also, another thing to note here is that only SPT blow count values are considered, but however, for real-world data sets, numerous types of measurements can be plotted within the profile plot, as shown. The layers created here will then be used in the next tab to create variograms. As the convenience to the engineer, profile plots can be exported into an Excel file at any time to allow for further examination or visualization simply by clicking Export here. Having included the desired collection of borings and having defined at least one soil layer, we can now continue rightward onto the Geostatistics tab. The single layer of clay defined previously is automatically transferred into the Processing and Controls of the Geostatistics tab, which in turn is used to build up spatial correlation structures for the defined layer. Owing to the relatively large data set, we saw that a few seconds of processing are required to process the tens of thousands of SPT blow counts and then form the various statistical data plots. We can now turn our focus to how spatial correlation structures packaged as variograms are formed. Let's start at the bottom left of the Geostatistics tab, and it's a layer-specific scatter plot of the SPT blow counts versus elevation. Scanning visually from left to right, the next plot is a histogram of the collection of SPT blow counts associated with the layer. While this synthetic dataset in the ensemble adheres to log normal distribution, real-world datasets may also tend to exhibit right-skewed distributions as shown here. Listed beneath the histogram plots are the mean, coefficient of variation, the variance, and the number of samples or the number of measurements positioned between the layer top and bottom elevations. The export feature here in this tab can be used to conveniently generate an Excel file of the elevation versus the SPT blow counts and the histogram for the associated layer. Continuing to visually scan from left to right across all the plots, we have now reached the main focus of the video, which is the variograms. Given that the spatial correlation is a 3D phenomenon, both horizontal and vertical variograms are formed. Conceptually, a variogram relates the distance between any pair of measurements, here SPT blow counts, to the strength of correlation between that pair of measurements. We refer to the separation between the pair of measurements as lag distance, which makes up the abscissa axis of the variogram plots. The ordinate axis here gives a normalized value typically between 0 and approximately 1 of the strength of correlation at a given lag distance. Note that the variogram ordinate value, as the variogram ordinate value approaches 1, the strength of correlation diminishes. For variograms values equal to approximately 1, the correlation is no stronger than the variance of the entire layer dataset. Note that there are two plots within each of the horizontal and vertical variograms. The diamond-shaped plots represent the experimental variogram points as obtained from processing of the site measurements and some basic variogram parameter inputs. The solid black lines are decided upon the engineer and are mathematical fits to the experimental variogram plots. So the diamond-shaped points constitute the experimental variograms, and the solid lines shown here constitute the theoretical variograms. Engineers can either supply values within the table above the plots to build up the theoretical variograms, or the theoretical fits can be established graphically by left-clicking and dragging within the plots. Because we are working with a synthetic dataset, the experimental variogram points are shown here well formed and in both the horizontal and vertical directions. That is that the curves indicate a relatively significant decrease in correlation at first and then followed by a clear asymptote. Therefore, we are able to use a graphical approach to create the theoretical variograms. For example, for the horizontal variogram, a normalized ordinate value of 1 is reached at approximately 10 feet, also shown here as in the horizontal range. For lag distances between 0 and 10 feet, the correlation decreases in a decelerating manner. For lag distances exceeding 10 feet, the variogram ordinates remain equal to approximately 1. Physically, this signifies that the synthetic dataset exhibits horizontal correlation up to approximately 10 feet of separation distance. For any measurements horizontally positioned greater than 10 feet apart, the correlation is no stronger than the variance of all the SPT blow counts within the layer. An additional consideration when forming variograms concerns the number of paired measurements identified at a given lag distance. As you can see, it's referred to here. The greater the number of pairs that are identified at a given lag distance, the more confidence the engineer can have in the variogram point. Clicking the variogram data button up near the top allows the engineer to view listings of the experimental variogram points for both the horizontal and the vertical variograms. As listed here, for each point, there is an associated number of pairs. The higher the number of pairs, the higher confidence in the measure of correlation given at a certain lag distance. Typically, we could see the number of pairs decrease with the increase in lag distance as shown here. And this also applies to the vertical as well. Summary data for each of the variograms are listed below the variogram plots. As I showed earlier, the listings include the number of points making up the experimental variogram, the minimum and maximum number of pairs, as well as the average. Note that the counts of pairs are relatively high for this demonstration model relative to what would be associated with the real-world datasets. Let's discuss some rules of thumb that may be useful when forming variograms using real-world datasets. First, please consult Chapter 2 of the Program Technical Manual for guidance on supplying base search parameters as supplied per layer in the table in the Geostatistics tab so that the program can identify pairs of measurements and form experimental variogram points, which are these diamond shapes as referred to earlier. Second, the number of pairs identified at a given lag distance should ideally be equal or greater than 30, or at least until the asymptote of the variogram curve is reached, which in this case we mentioned earlier was 10 feet. Also, both horizontal and vertical variograms should always be initially considered when investigating the spatial correlation of site data pertaining to a given layer. For relatively limited datasets, only vertical variograms may be formed, where this topic will be the focus of another video. However, both horizontal and vertical variograms can be formed, like in this case. The ordinate values at which the experimental variogram points appear to converge should be approximately equal. As shown here, they appear to converge right about 1. Otherwise, it may be the case that the underlying data associated with the layer contains measurements from multiple geological zones. For real-world datasets, it is typically necessary to define multiple layers here along the profile. The variograms must then be formed for each individual layer. Once all the variograms have been formed, be sure to click the Process Layers button here before proceeding onward in the program. That concludes the current tutorial, which is focused on variograms. Stay tuned for more on GeoStat.